Geology of National Parks class. Let's have a lecture on Mammoth Cave and Carlsbad Caverns. These are national parks that have been shaped by groundwater. Groundwater is just water that's found in the ground, right? Found in all the pore spaces, fractures, crevices, and voids in the ground, in the bedrock. And groundwater is important to humans and civilizations because it's the largest and easily accessible, ready to use water resource for us. And it only makes up 0.6% of the hydrosphere. But in terms of liquid fresh water, it's 94% of liquid freshwater reservoirs. So that's really important. So if you take a look here, of all the freshwater on Earth, of all the water on Earth, only 2.5% is freshwater. And so of that 2.5%, okay, most of it is locked up in ice sheets and glaciers, okay. About 30% is groundwater, okay. So that's this right here. But if you think about liquid fresh water, so that it doesn't include any ice or snow, groundwater makes up about 96% of all fresh water on Earth. So that's why it's a really important resource, especially here in Florida. So every day we use about 350 billion gallons of fresh water, and 23% of that comes from groundwater. And it exists almost everywhere, and that's why it's advantageous to use it, especially in areas where surface waters aren't readily available. And groundwater is mostly used for irrigation. Okay, so if we look at water as a basic resource and how it's being used, most of the country uses surface water, so that's 77%. Okay, that's all this here. 23% of our water use is groundwater, and most of that use goes towards irrigation. Okay, so that's around 68%. Most groundwater arrives to the ground via precipitation. Rain or snow kind of falls onto the ground and slowly infiltrates and then becomes part of the groundwater system. And as it does so, it moves through the top surface, which we call the zone of soil moisture. That's where water is held in that layer only by molecular attraction in soil particles. And this is the moisture that's used up by plants. A lot of times this will evaporate directly back into the atmosphere. And if water is not held in this zone, it percolates downwards into the unsaturated zone, or the vadose zone. Okay. If you go anywhere in Florida or and just start digging, eventually you'll reach the zone of saturation. This is where all the pore spaces are completely filled with water. And what you'll notice, if you dig that hole, water will start to pool, and that's what we call the water table. All right, the zone of saturation is also called the Phreatic Zone. And it, depending on where you are, the depth to the water table, or how far you'd have to dig to get to the water table, varies. When I worked at an environmental consulting company in Fort Lauderdale, we'd often have to go into Miami, and in Brickell, or downtown Miami, the depth of the water table is only about 1.5 feet. That's nothing. That's really close. So those areas of Miami can flood fairly easily. In other places, it could be 10 to 15 feet before you hit the water table. Okay, and as you're digging, that 10 to 15 feet is called the vadose zone. That's the area above the zone of saturation. So here, the pore spaces are filled with both water and air. And that includes this, there's an area called the Capillary Fringe. And that's where groundwater is held in pore spaces by surface tension. It's a lot like when you spill some liquid on a counter and you use a paper towel to clean it up. What you'll notice is that once you lay the paper towel on the liquid, the water will start climbing up the paper towel. It's because of the high surface tension. It kind of fights the force of gravity and moves up the paper towel. That's kind of like the capillary fringe. So right before you get to the water table or the saturated zone, you'll run into a fairly wet area here called the capillary fringe. Here's the zone of soil moisture, okay? And then this whole area here is the vadose zone. So it has pore spaces filled with water and with air. And then once you get to this area, the zone of saturation, this is where the groundwater is, and every available open space is occupied by water. And so if we look at a cross section of some landscape, we've got like a valley, okay, with some hills here. This would be the water table, and the water table is kind of like a subdued replica of the landscape, okay? And where the water table intersects the land surface, you get groundwater discharge. So the groundwater discharges into this river. All right, and then the water table fluctuates, and it fluctuates depending on the weather, right? If you have rain events, that means the water table will go up. And if you have times when there's no rain, then the water table will actually fall. So the water table is variable, okay? And then we build wells to access that water. That's what wells are. So the depth of the water table varies seasonally, year to year, month to month, rain event upon rain event. The shape of the water table, remember, think of it as like a three-dimensional surface underground, and that kind of undulates and moves up and down and kind of mimics the landscape. Here in Florida, because it's so flat, essentially you can just imagine almost like a flat horizontal plane undercutting the ground. Think of a retention pond or a lake that you live close to. Maybe on Osceola campus you can see the retention pond in the front of campus. Look at that horizontal layer of water, and then imagine that cutting across under the ground. That is the approximate location of the water table. That's a good way to estimate it here in Florida. Okay. So here is an example of how we monitor the water table in different areas. This is the state of Missouri. There are a bunch of different wells here, and these wells are hooked up with a radio antenna, and so it collects data onto the data like the depth of the water table as an example, and then it sends that information to someone on their computer, and they can plot this. And they can plot it over time. Here on the x-axis we have months of July to March from 2006 to 2007. And then here is the depth to the water table. So here it's 61 feet. So that means you'd have to dig 61 feet in the ground to reach the water table. Okay. But then this area of Missouri, and we're talking about this well here, right? This area of Missouri, what they witnessed was a lot of dry weather. And so what happened is the water table started to fall deeper and deeper up until about maybe almost 67 feet. So now you'd have to dig 67 feet to get to the actual water table. And then over here there were a few rain events in November, all right, and January and April. And what happened is the water table rebounded because of all that precipitation. And so the water table rises and falls depending on how much it's raining. And we can map that surface of the water table. If we have a lot of data, a lot of different wells, and we can collect data as to like the depth to the water table, then we can contour that surface underground and figure out which direction the water will flow. Water flows, or groundwater flows exactly like runoff water, or water that runs on the surface of the earth, like rivers do, under the force of gravity. But because groundwater is moving through bedrock, it moves much slower. So here's an example of a bunch of different wells that they give you the elevations above sea level. So this is a really high spot, and these are lower spots. So this is 151 feet above sea level. This is only 106 feet. So imagine here, this is higher than this over here. So if we plot contour lines of equal elevation, so 140 feet above sea level, 150 feet. The way you figure out the direction of groundwater movement is drawing a line that's 90 degrees to one of those contours. And so this is the direction of the groundwater flow. Now groundwater flow is pretty slow. It's about, on average, 4 centimeters per day. So that's kind of slow. So this is the direction that the groundwater would flow in. And that's really important because you could have, like, let's say a landfill over here, right? And landfills oftentimes leak contaminants into the groundwater. And so if that happens, those contaminants will move in this direction. So it'd be a bad decision to build a school over here, because then they'd be in the direct path of these contaminants, especially if the school's using a well to draw up its water. That's a no good situation. So that's why it's important keeping track of the direction of groundwater flow, and also what's going on the surface in terms of properties and land use and stuff like that. Groundwater and streams can work together. Groundwater can contribute water to a stream. We call that a gaining stream. But if the groundwater table is too low, then streams can lose their water to the ground and contribute to the groundwater. So a lot of times rivers are kind of what we call combination streams, in the sense that during rainy times they're gaining streams, and during dry times they might be losing streams. Let me just go to the images. This is an example of a gaining stream. So here's a river, okay, water flowing. Now here the water table is pretty high, and what we notice is the water table intersects the land surface right here. And so what that means is that groundwater is going to discharge into the river. So it actively contributes water to the river. And that's great, because sometimes it won't rain. And if there's no rain, the water in a river can be replenished by the groundwater. In other situations here, this is the water table. And if you notice, the water table is lower than the river water here, and lower than the river. So what's going to happen actually is that water from the river is going to move into the groundwater system. Okay, we call that a losing stream because it's losing water to the groundwater reservoir. And then here, this is a completely disconnected losing stream, and this typically happens in fairly dry landscapes. So the water table is way below the river itself, and so the river will just continually lose water to the groundwater system. There are a lot of factors that influence how much water can be stored in the ground and also how it can move. Porosity is the percentage of pore spaces in a rock or sediment. Okay, so I want you to think of one of those orange Home Depot buckets. Picture that in your mind's eye, and then fill that up with golf balls. And those golf balls kind of represent sediment macroscopically, right? You can think of sand-sized sediment microscopically, and it's the same purpose. But you fill up that orange bucket to the brim with golf balls, and you can't fit anything else in it, right? The bucket is full, but you could fit water in it, right? You could just start pouring water into that bucket, and you could fill up a lot of water into it. And that's what porosity is. And those golf balls kind of represent kind of small sand-sized sediment or larger sediment or the clasts that are in sedimentary rocks. So it represents the pore space that's within those clasts. And that really determines how much water can be stored in one of those sedimentary rock units. So here's an example. Say we have a beaker filled with a bunch of sediment, okay? And then we start dumping water in it, okay? And then we dump water in it until the water is completely saturated and is sitting on top, almost as if it's flooding the sand itself. And then we can measure the amount of water we poured into that beaker. And in this case, it's about 500 milliliters. And it's in about 100 milliliters of sediment, which means the porosity or pore space represents about 50% of the volume of the sediment. Okay, so that's how we measure porosity. And if you have sedimentary rocks with clasts that are all very similarly sized, kind of like the golf ball example, that's going to have great porosity. There's going to be a lot of space in between each of these kind of similarly sized sediment. So that typically, when you have, that's called well-sorted. Well-sorted grains, meaning that they're all about the same size, will have very high porosity. If you have something that's poorly sorted, meaning you have grains that are, some are pretty small like these over here and some are pretty big, what happens is those really small ones eat up all the space in between the larger grains, and that contributes to lower porosity. So something like this can hold less water than this one over here. Another factor that influences especially the movement of groundwater is called permeability. And permeability is the ability of something to kind of transmit a fluid or allow it to flow through the host rock. Okay, and so that is dependent on how those pores are connected, the connectivity between those pores. If you have good connectivity, that means you've got great porosity. And so if you have that, if you've got good porosity and decent permeability, what you'll have is a reservoir of water that's can transmit groundwater freely, and we call that an aquifer. Okay, in South Florida, the aquifer down there is called the Biscayne Aquifer, and then here in Central Florida, our aquifer system here is called the Floridian Aquifer, and that is we have permeable rock, bedrock, that can transmit groundwater freely, and so we can build wells and access that water. If we have a geologic unit that is impermeable and doesn't allow water to move through it, we call that an aquitard. So here's an example of an impermeable unit here. A lot of times things that are impermeable are like clay or silt sediment, because they're very flat and they kind of pancake on top of each other, and they don't allow water to move through them. So this would be an example of an aquitard. Okay. Over here, this example in the middle here, you can see that there's a lot of pore space, right? So this has great porosity, can store a lot of water, but those pore spaces aren't really connected. So you actually have low permeability, non-permeable. And then this third example here, you can see a lot of pore spaces, and the pore spaces are connected. So you can see I can kind of draw a line through all these pore spaces. That means the water's available to kind of transmit freely through this material. So this is porous and permeable. So this would be an aquifer system. So how does groundwater move? Well, it moves very slow, 4 centimeters a day. It's a glacial pace, right? So that idea that groundwater is involved with like underground rivers, that's a really rare and common misconception. Although when we talk about Mammoth Cave, they do have underground rivers. So I guess we tend to show you the exceptional cases. But here, this image down here shows you a simple groundwater flow system. Okay, so typically here's the water table, and this is at a higher elevation than down here. So the groundwater will move under the force of gravity in this direction, downhill. Okay, and then when it intersects the land surface, we call those discharge areas. And then areas that receive the rain over here, we call them recharge areas, because of the areas that are kind of recharging the water into the groundwater system. And the way we measure groundwater movement, there's a formula for that. It's called Darcy's Law, and it measures the volume of water flowing through an aquifer. And what's needed in order to determine that is the hydraulic gradient, the conductivity. Those are the two main factors. Okay, the hydraulic gradient is essentially the measuring of the water table slope. Okay, so let's say we have a well here, and it's at a higher elevation, and then we have a well here, and it's at a lower elevation. Okay, so the greater the difference, that means the greater the hydraulic gradient, and the faster the water could potentially move, because it's also dependent on conductivity. But in order to measure the gradient, what you have to do is subtract the height difference between the first water table here and then the second water table at H2, then divide it by its distance. And that gives you the gradient. If you have a higher gradient, you'd potentially have faster moving groundwater. If you have a lower gradient, then that would be slower moving groundwater. The other variable that's really important is conductivity, and that is a measure of the permeability of the rock of the aquifer. So if something is very permeable, that means the water will be able to move at a faster velocity. If there's something that's not very permeable, then that means that water will move a lot slower. All right, wells are essentially just holes in the ground that we bore into, and modern wells, they're either, a lot of times they're just 2 or 4 inches in diameter, and it's just PVC pipe that we just place in the ground past the zone of saturation, and then we run tubing, and then we pump water out. And that's how you can access groundwater. It's a very common method for removing groundwater. And there are more than 16 million water wells in the United States. Maybe you have your own water well if you live away, off city limits. And there's good and bad things. I've heard a lot of people complain that their water is kind of swampy, or they have hard water that's coming from their well, or kind of smells a little sulfury. But the benefits are, you don't have to pay a water bill. You don't get a bill from a utilities company. You can use as much or as little water as you want. But remember, always conserve. Don't just sprinkle your lawn all day and have the greenest grass just because you're not paying a water bill, right? And so 13 million wells belong to private households. So many of you probably have your own well. Now, what happens if you pump too much water out from your well, you'll draw it down. And that can actually lower the surrounding water table. And that creates a cone of depression. All right, a cone of depression is when you lower the water table down. Let me just show you an image. And you can actually change the hydraulic gradient. So let's imagine a scenario where we've got two neighbors, one here and one here. They're growing some crop that needs a lot of water, so they built a new high-capacity well so they could pump out as much water as possible. But when they do that, they will artificially lower the water table and create this cone. So you see that? That's the cone of depression. Favorite flavor of ice cream, right? And what happened is that neighbor here, now their well runs dry because they've lowered the water table. And so that could be detrimental to people around. You gotta be a good neighbor. All right, aquifers. There are two types of aquifers. There are unconfined and confined aquifers. They both come with benefits and drawbacks. The Biscayne Aquifer is an unconfined aquifer. And what that means is the land surface, or when it rains here, the precipitation can directly recharge the unconfined aquifer, meaning that the unit above the aquifer is completely permeable. Okay, and that's a good thing. Why? Because that means this aquifer, this unconfined aquifer, can recharge fairly quickly and locally. Okay, so when you drill a well into it, the water in the well will rise up to the water table, right? Everything's unconfined. It's not pressurized. But the bad thing is it's because it can get because that upper layer is permeable, it can get contaminated easily. Meaning, like, if you have a gas station with those huge gas tanks underground and they start leaking, that gas will leak directly into an unconfined aquifer. And you don't want to be drinking gas water, do you? Confined aquifers are where the water can be pressurized. Okay, and so what's happening here is that you have an aquitard above and below the actual aquifer, so it's confined. Now that's a good thing, because if you have any gas stations or landfills, anything that could potentially be hazardous to the groundwater, then that contamination won't reach the confined aquifer. That's great. The problem is confined aquifers, they don't recharge as quickly as unconfined aquifers. So in some cases, if you pump too much water out, you could potentially just drain it, okay, or just lower the water table. I mean, it wouldn't be the water table, but it's just the confined aquifer water level. So yeah. So, and a lot of times, confined aquifer, especially if it's an inclined one, say the aquifer is like this and then it goes upwards like that, it has to be recharged somewhere. So if it's recharged at a higher elevation, so it rains over here, that provides a lot of pressure. That water that's moving downhill under the force of gravity provides pressure for the water here. So if you tap into that in a well, the water table, the level of the water will rise because the water is pressurized. And that leads us to artesian system. Artesian systems are like an artesian well or a spring is a system where groundwater that's under pressure rises above the groundwater level and out of the aquifer. And so you got two conditions have to be met in order to have an artesian system. It must be a confined and an inclined aquifer. And and we call those a confined aquifer, Artesian system. Here's an example. Look, there's a pipe, PVC pipe coming out from the ground, and water is just coming out, and that's because it's under pressure, and the water is just going to continually coming out until you cap this. There's two types of Artesian systems. There's non-flowing, and then there's flowing. And not all Artesian systems are artificial, meaning like we didn't build a well and this is happening. A lot of the desert oases that we see are the result of groundwater discharging from a spring because of perhaps a confined aquifer. So let's take this as an example. Let's pretend this is North Florida, Tallahassee area, and then this is Central Florida where we are. They're at a higher elevation, albeit not much, but they're at the kind of foothills of the Appalachian Mountains. And so here's your confined aquifer. You have a aquitard above and an aquitard below the confined aquifer. So if it rains here, that'll recharge the aquifer here, and then this provides the pressure for the water in this area of the aquifer. So if you were to build a well over here at this site, right here, this would be an Artesian system, but we'd call this a non-flowing one because the water rises above where the water table is locally, but it's not flowing out of the well. Okay. Over here at site number 2 in Central Florida, if you built a well, the water would come gushing out. And so you wouldn't even have to pump and run tubing. You just have to cap this well and just let it slowly come out whenever you need it. But this water will just continually come out. That's a flowing Artesian system. And there are places where this occurs naturally, and we create these. Engineers create municipal water towers. That's why we store water towers up high in an elevation. Maybe you've noticed the St. Cloud water tower. That acts as the quote-unquote recharge area, and the pipes are the aquifer, and the faucets are the flowing Artesian wells, right? Because we want that pressurized water to wash our hands, right, and get the shampoo out of our hair. Okay, so here's your classic Artesian system. This is in South Dakota, real example, west to east cross-section across the Missouri River. And on the west side, there's this recharge area at a higher elevation. So here's a permeable Dakota sandstone. So when it rains here, that water kind of infiltrates and becomes part of the groundwater system. And if you go to the east side of the Missouri River and you build a well over here, it's at a lower elevation. So here you'll have natural flowing Artesian systems. All right, and here's your water tank example. We store water at a much higher elevation because this provides a pressure surface. So when you turn on your shower or faucet, you have pressurized water. All right, and then that leads us to springs. This occurs naturally. Here's a picture of Jenny Springs. Maybe you've been there. I'm sure many of you have been to Wekiva Springs. I lived in Tallahassee for a while. Wakulla Springs is pretty nice. And springs are just groundwater discharging. And a lot of times in Florida, that just discharges into low-lying areas, and they become rivers. We have a lot of spring-fed rivers. And I don't know if you've been there. Maybe you can nod your head and agree. Yeah, the water can get pretty cold. And that's great in the summertime, right? Because it's so hot out and you get into some really cool spring water. Rainbow Springs, I don't know if any of you guys have been here. Again, spring water just discharges from our limestone bedrock, and then a river is born. And these are beautiful areas. I really recommend visiting a lot of different springs. Blue Springs is beautiful. You got manatees moving up in there in the wintertime. All right, so this brings us to the biggest of them all, Mammoth Cave, Kentucky. Okay, if you're ever going into Kentucky, this is a cool place to go to. It was used by Native Americans 3,000 to 4,000 years ago. Early in American history, it was mined for saltpeter. Saltpeter is bat guano. Okay. It was used for making gunpowder because it's almost like fertilizers, like nitrates, so you can use that to blow stuff up. So it became, when it was discovered, it became a really early tourist attraction in the 1800s, and then officially became a national park in 1941. It's the largest known cave system in the world. over 300 miles of explored and mapped passageways. Here's some satellite images of the entrance to Mammoth Cave National Park. You can tell that's a parking lot. But here, look. Here, let's move on. There's a river that cuts right through this area. All right. There. This is a ground view of what you see there. Okay. Unsuspecting, you wouldn't think there's 300 miles of caves here, but there are. And the cave is developed in the St. Louis, the St. Genevieve, and the Gherkin limestone formations. Notice that they're limestone. Limestone is a rock that dissolves away with a little bit of carbonic acid, which is normal in groundwater and water that's infiltrating through the ground, and that slowly dissolves it away. And that's how these caves form. These units are old, Mississippian in age, and they correlate with the Boone limestone in Arkansas and the Redwall limestone in the Grand Canyon. I don't think we've ever talked about the Boone limestone, but we definitely have talked about the Redwall limestone in the Grand Canyon. That's a very thick unit that's noticeable when you look out onto the canyon. About 345 miles of passages, and the ones that are open to the public are about 12 miles. That's a lot. So if you go here, the temperature within the caves itself typically ranges from low 50s to maybe 60s. That's nice. So 12 miles, that's a hike and a half that you can go in there and visit a lot of these places. Okay, the deposition of the limestone occurred during the Mississippian period, which was 350 to 325 million years ago. And the deposition of detrital rocks occurred later in the late Mississippian and Pennsylvanian, followed by slow subaerial weathering in the late Paleozoic. So that's much later. The forming of the cave itself occurred in the Tertiary about 10 million years ago. So it took about 10 million years for the caves to develop to where they are today. And the lower cave levels more recently in the Pleistocene epoch. Okay, here's a cross-section of the area. So the ground level shot that I gave you was, like from hillsides over here. This is the Green River, the river that we saw kind of cutting through the area. Here's the Mammoth Cave Plateau, the Pennyroyal Plain, and then there's the Dripping Springs Escarpment. So this is kind of like a cliff area where water kind of a lot of times can discharge out, or especially on this side because the way the rocks are tilted. But here's the labyrinth of passageways and cuts all the way through these different units of limestone. You see here there's the Warsaw limestone, here's the St. Louis limestone, above that the Genevieve, and then the Gherkin closer to the top. And then there's some younger units up here that we'll talk about. But yeah, it almost looks like an anthill with all the little passageways. Okay, so here's another cross section. This is the Chester Upland area, so higher elevation. Here's the Pennyroyal Plateau, low-lying areas. You can have knobs. This is what we refer to as areas that of rocks that haven't been eroded away. This occurs through differential erosion, so other areas erode faster than others and leave behind knobs. And then here are those units, the St. Genevieve, the St. Louis, and then this is just a kind of an estimate of where the caves are, cave entrance, and then you can kind of go around and look. And there are springs or groundwater discharging from areas. This is the cross section of the Green River. Okay, here's another view of a lot of the different cave passages. Remember, it's multi-level. It's almost like multi-level Swiss cheese, just holes and caverns and passageways all over the place. Okay. So here are the Mississippian limestones. Above here, these are the Mississippian cap rocks, the Big Clifty, the sandstones up here. Then below here, these are those three limestone units. The Gherkin, which is a little higher in this area, that's about 200 meters. And that was active more than 3.2 million years ago. Okay, and then this level here developed over millions of years. Okay, It was active more than 3.2 million years ago. And then this is some of the large cave passages you can find here at a depth of about 180 meters above sea level. Okay. Here's the modern level of the cave where the groundwater and river water are about the same level here. This is where the current excavation in the Green River is about going, and that's only about 128 meters above sea level. All right, this level was abandoned about 1.2 million years ago, but there were a bunch of episodes of dissolution of the limestone here to create these large cave passages. So here's a cool cross-section of Mammoth Cave. Here's the park map, which is pretty cool. You can zoom in and take a look at it. This is the yellow area is what's open to the public. They show you a couple of different entrance. Oh no, I'm sorry. Here's the visitor center, and you can visit these areas. Here's a big drop off. I'll show you the big the picture here in a second. But I don't know if you've ever been to a cave before, but a really cool exercise is to turn off all your lanterns and experience the darkness of the cave. And I don't think you've ever experienced how dark a dark cave is when there's zero light, and it's almost calming. Okay, so there we go. Here's a closer look at the different. Here's the historic entrance, where they used to run tourists in the 1800s. This is the Mammoth Dome. Okay, this is an area you can look down from the Mammoth Dome, and it's an immense vertical shaft, very deep. I forget exactly how deep it is. But yeah, that's it right there. And then you can see you can walk through all these areas. And when you get to the lower levels, you actually have underground water flowing in river, which is rivers, and this is pretty cool. Here's they have funny smaller passageways. Fat Man's Misery. Here's the bottomless pit. Okay, so very complex labyrinth. All right, so this is what it looks like on the outside when you're looking at that bottom level, where the kind of like where the Green River water level is, and you can look at different cave entrances from this area, where it's inundated with water here. Here's the bottomless pit, Mammoth Cave. Just straight down. You can't see the bottom because it gets too dark. Yeah, so it's about 200 feet, this vertical shaft in Mammoth Cave, where the bottomless pit is. And just to get an idea of the different passageways in this cave, some of them are less than 10 feet wide, but they range from about 100 feet high. So you get all kinds of areas. Some parts of the cave are broad canyons as much as 80 feet wide. So this cave system has a wide variety of different passageways. And the way these passageways form is through the dissolution of limestone. And essentially, groundwater has a little acidity to it. It contains carbonic acid, and that dissolves limestone. And so here's the dissolution, or carbonate dissolution. So when you have meteoric water or rainwater, groundwater that combines with carbon dioxide, which is in our atmosphere, you create carbonic acid right here. And then this is limestone, CaCO3 or calcite, and that combines with carbonic acid, and then you release calcium into solution, and you create bicarbonate ion in solution. So essentially you're taking something that's a solid and then creating a solution. Man, I really made a mess of this. Oh God. All right, let's move on. So the acidic groundwater slowly dissolves the limestone, and the dissolution can happen both in the vadose zone or the unsaturated zone, or even in the saturated zone. So tiny little fractures in the bedrock slowly become enlarged. If you actually have turbulent flow, which is the case in Mammoth Cave, abrasion can make those fractures larger. And the approximate rate of dissolution is 0.01 to 0.1 centimeters per year. I know that doesn't seem like a lot, but we're talking about cave formation over millions of years. So if you multiply that in millions of years, that means you have kilometers of material that's being dissolved away. All right, here's an example of something similar you would see in Kentucky and in Florida. This is a sinkhole and a losing stream in Paynes Prairie State Park. So what you have, a sinkhole is essentially an area where you have the dissolution of limestone that's accompanied by a collapse. And then a lot of times water will just fill up and it'll become a lake. And Florida is covered with these circular lakes that were sinkholes at one point. And what will happen is sometimes streams, if they move across limestone bedrock, they can just sink and disappear. And that's the case here in this park and also in Kentucky. There are a lot of losing springs that just disappear into the ground and into limestone, as well as water that just discharges. Like if you go to any of the escarpments in near Mammoth Cave, you can see water just discharging off the side of the limestone and being like a spring that might feed a little creek that runs into the Green River. So water in that system in Mammoth Cave moves through fairly quickly, and a lot of water moves through this limestone, highly porous limestone. If you look a little closer, these aren't logs, those are actually gators. So don't go swimming in that water. All right, so these type of landscapes are referred to as karst topography. That's a landscape that's been shaped by that dissolving power of groundwater, which is like carbonic acid eating through that limestone. And what it creates is an irregular terrain, and it creates what I refer to as sinkholes, dissolving bedrock accompanied by collapse, and then it can leave kind of crazy surface drainage and sinking streams. And you can also have a landscape with tower karsts. Those are huge knobs of highly fractured and jointed material that's left behind from the dissolution of groundwater. So here's the development of a karst landscape. Think of this as the development of the Mammoth Cave region in Kentucky, is that over time, 0.1 centimeters per year, this groundwater will dissolve away this limestone and create all kinds of caverns and passageways and holes. You have sinkholes forming perfectly circular that collapse downwards, sinking streams, escarpments like we see there, right? Here's like the Green River where we see springs just coming out of areas like this. So this is typical karst landscape. And here's a sinkhole here in Florida. Imagine that luck. You can get sinkhole insurance just in case something like this happens. Notice the sinkhole is perfectly circular. That is really bad luck for this family that this happened to. Hopefully no one was hurt. But if you notice the house next door, their neighbors, yeah, that's a moving truck. They're getting out of here because that's pretty scary. All right, in case you were wondering, this is the Florida Geological Survey's risk assessment map of Florida, the different counties in Florida, and how risky it is or how prone an area is to sinkholes. And I'm imagining most of you either live in Osceola, Polk, or Orange County, okay, in this region. If you live in Polk County, that's red. That's very high sinkhole-prone regions. Like I said, you can buy sinkhole insurance for your home. Okay, some of the areas that are really hard hit, Pasco and North Hillsborough County, there are a lot of well fields there that pump a lot of water down, and that can cause sinkhole formation. So this is a real problem that we deal with in Central Florida. Here's another dramatic sinkhole. This occurred in Guatemala City, Guatemala. Surprisingly, nobody died here, and this was the capital of Guatemala City, and there's like 5 million people that live here. This was caused by water leaking from a pipe that was burst, and then it caused this collapse. Pretty crazy. And so if we look at a shaded relief map of the Osceola Plain, where our campus is located, right, this is East Lake Tahoe, so a little further north to Orange County. A lot of these circular lakes that we see, Lake Tahoe, the reason why they're circular like this is because they were a sinkhole, right? These are all former sinkholes. A lot of times here in Florida, because the water table is so high, you get a collapse, right? And then that fills up with water, and then that becomes a lake. And that's the origin of many, many lakes that we see in Central Florida. Okay, so let's talk about some of the features that form within the caverns of Mammoth Cave. Call them speleothems. They form in the vadose zone, or that unsaturated zone, and as water trickles down through the unsaturated zone to kind of join the saturated zone, the reservoir of groundwater, it kind of drips through, and calcite is deposited through this dripping water. So as that water evaporates, it loses its carbon dioxide, and then it crystallizes that calcium carbonate right on the tips of these speleothems. And so the stalactites are ones that hang from the ceiling, and stalagmites grow from the ground up. And if they meet each other, then you'll have a column. All right, so this is a column of a stalagmite and stalactite growing upwards from both directions and meeting. This is a stalactite. You'll see that. Here's one growing from the ground up, which is pretty crazy. And then this is a shield. So it's like kind of a lot of them kind of flowing down. It almost looks like melting candles, okay, coming downwards. It makes for a very peculiar and interesting environment when you're in a cave and you see these kind of things. So here is the frozen Niagara in Mammoth Cave. Beautiful column of just water trickling down and precipitating calcium carbonate here, and creates these features that take thousands of years to form. So this looks like kind of like a melting candle downwards. It's beautiful. Here's some other features from Mammoth Cave, more stalactites. All right, let's move on to Carlsbad Cavern and Lechuguilla Cave. This is in New Mexico. And it has a little bit difference in terms of its geologic history. It developed in limestone of Permian age, and it didn't form by the dissolution of carbonic acid. It formed by the dissolution of sulfuric acid. So it has a little different story to it. The hydrogen sulfide from oil deposits oxidizes to form sulfuric acid, and that's a bacterial-driven reaction. So the bacteria are involved in that type of work to create sulfuric acid. And the calcite here, or the calcite in the limestone, that's part of the bedrock here in New Mexico, is dissolved by that sulfuric acid, and that produces gypsum as a product. And so gypsum is an entirely different material, right? So a lot of in Mammoth Cave, you get a lot of stalactites, stalagmites, just made up of calcium carbonate. But here we have a lot of gypsum forming, and gypsum's a distinctly kind of white mineral, which is beautiful. Okay, so here's that chemical reaction. And so in Carlsbad and Lechuguilla, they have speleothems, or cave-type deposits that are made of gypsum. And gypsum's very soft and can crumble easily, so they're very delicate. And here, they're over 107 miles in length in terms of the cave here, so not as long as Mammoth Cave, but 1,593 feet deep. Okay. These are the largest underground rooms of any cave in the United States. So there are a lot of different cave formations here. And the passages move through a massive reef limestone. Okay. And right now it's like Mammoth Cave continues to be kind of slowly dissolving away and enlarging year by year. Carlsbad Caverns is no longer being enlarged. So you can find this here in New Mexico. Here's a satellite image, a little closer up. You can see the landscape's a little drier. There's Carlsbad Caverns. Here's the park map. Okay, you can actually take an elevator down to some of the rooms down here. They have a cafeteria in the big room. I'm saying, like, this is the big room. Okay, this is the equivalent of 4 football fields together. and the height of the ceilings are about around 200 feet. So you can get in an elevator if you don't want to go through the natural entrance and walk it. There's a bat cave here, and natural bats come out, and the farmers like it because they keep the insect populations down, which is great. But here's the natural entrance. You can go down this way, very long distance, or you can just take the quick elevator down 1,500 feet. It's a long elevator ride, and then you get down the big room again, 200 feet high. It's almost like a cathedral. This place is big. It's roomy. Okay, and just to get some perspective, this is the Needle building in Seattle. That's about how deep you are underground. Kind of scary, huh? So here's what the if you're on the ground, what the environment kind of looks like. It's New Mexico, so it's dry, desert, kind of steppe landscape. Here's the natural entrance. Okay. So the geologic history of this area is that is deposition of limestone in the Delaware Basin during the Permian, which was 300 to 250 million years ago. And so the first development of the karst landscape development happened when sea level dropped in the late Permian. Then that basin was filled with gypsum due to the high evaporation as sea level fell. Then there was tectonic uplift and deformation in the Cretaceous. So that's more recent times. And that's when the early cave development occurred. There was renewed uplift when the Guadalupe Mountains formed in the late Tertiary, and that accounts for major cave developments. And then the draining of the caves occurred in the Pleistocene, and that's when we saw the deposition of the gypsum speleothems. Okay, so here's kind of a cross-section of the area. Here are the here's the big room. Okay, there's a canyon above here. This is the cave entrance. All right, so here you can get some elevation. Sorry for the blurry image, but it's the best I could find. Look at that. Look at those speleothems. So this is a gypsum column, essentially. So that's that white color. Absolutely beautiful. It's well lit. It really is like just like you're walking into a completely alien landscape. Absolutely beautiful colors. A lot of different cave formations in this unique cave structure. The last image was when you saw the kind of large stalagmites. That was the Hall of Giants, and they kind of grow outwardly as water kind of trickles down around them and evaporates, and it's almost like adding a thin coat of paint every 65 years. All right, and a lot of these stalactites hanging from the ceiling have kind of like icicle shapes. You do see some deposition of calcium carbonate. Here's a GPS mapping of the different cave passages you can go through. This here is Lechuguilla Cave, and this wasn't found. This was almost accidentally. Well, no, they were exploring a certain area, and then this beautiful area. This is not accessible to the public because of how rare this area is. Let me show you some pictures, but there's one room called the Persian Gulf Room in Lechuguilla Cave, and it was accidentally discovered when cave divers decided to investigate the bottom of a 90-foot pit, and so they had to crawl through an area, and they popped out in an entirely new area, and it looked like this. There's one of those cave divers, kind of lit up a little bit, but look, what is this? Is crazy. So these are these flat-lying, rimmed, what are these called? These are the dripstone pendants, which form that way. So it's a very unusual cave formation in Lechuguilla Cave. You can see huge aragonite and gypsum formations within this cave, which is bizarre. So here's some more gypsum or aragonite and gypsum forming. Okay, so that's that white. These are very fragile. So you can see how big they are. This is a regular sized cave. Explorer. There's another shot of these beautiful gypsum kind of crystallizing from these voids in space. All right, so that's Carlsbad Caverns. It's one of the most visited national parks in the U.S. It's very easily accessible. It's got an elevator, so that makes it easy. Yeah, you can check it out. All right, so that's. I guess I failed to mention too, in Carlsbad Caverns, the source of the oxidizing sulfur that turns into sulfuric acid are the oil deposits underground. So the bacteria that oxidize the sulfur, they're doing that from those oil deposits. So that occurs, and so those are two amazing cave systems, but they form in two different ways. One through the dissolution of sulfuric acid in Carlsbad Caverns, and the other is carbonic acid, which is the more common form in Mammoth Cave. All right, let's talk about the environmental problems with groundwater. We really should be treating groundwater as a non-renewable resource, especially in places like out west. There's not a lot of surface water out west. It's a lot drier, so they a lot of times depend on groundwater. In areas in the Midwest that overlay the High Plains Aquifer, that's about 111 million acres of a lot of mostly farmland that overlays the High Plains Aquifer. It's the most agriculturally significant aquifer because that's where they pump out all the water for that. And that accounts for about 30% of all groundwater used for irrigation. Here's an image of the High Plains Aquifer. And what the colors indicate are anything in red is where the water table has fallen over 150 feet. 150 feet, so that's 15 basketball hoops stacked on top of each other. So that's a lot. That water table has dropped a lot, and that's because people there are pumping a lot of water out. It's especially dry West Texas and Oklahoma and Southwest Kansas. This area is very dry, so they're using up a lot of groundwater to sustain their farms there, and that's causing the water tables to fall. In some areas in Nebraska, they're actually seeing an uptick in the water table. Okay. Now the problem with that is that if you pump out too much water from the groundwater reservoir, you'll have subsidence, and the ground will sink when water's pumped out. Think of you're replacing the water that's underground with air, essentially, as you pump the water out. So all those pore spaces, instead of being filled up with water, now they're filled up with air, and air is compressible, right? So that's why the ground sinks, right? Because it's you're adding all this weight above it. You're pumping out the water, which is like its support, and then you get subsidence. In some areas, it's been quite drastic. In the San Joaquin Valley, about 30 feet or 9 meters of subsidence have occurred. In Mexico City, which was built on a lake bed, it's really dry there as well. They pump out a lot of water. There's about 22 feet of subsidence, or 7 meters. And so a lot of the buildings in Mexico City, the older buildings, their first floor is now the basement, and the entrance is now the second floor. They've sunk so much. Okay, here's the San Joaquin Valley. This is where we grow a lot of alfalfa, almonds, and other vegetables in this valley, very agriculturally active. But this was the ground level in 1925. Today, the ground level is down here. That's insane, right? 52 years of heavy pumping and about 30 feet of subsidence. More immediate and drastic things can happen if you pump too much water out. You can have collapses like this. Okay. Another environmental issue with groundwater that's important, especially to coastal Floridians, is saltwater intrusion. This is where if you pump out excess groundwater, it'll cause salty seawater to infiltrate and move inland. And that's occurring today in South Florida. If you build a well anywhere east of I-95, you're getting salt water. So all the well fields are kind of built out west, kind of like near Plantation, closer to the Everglades. So fresh water is less dense than salt water, so it kind of sits above the salty groundwater, right? So if you have a well, and if you start pumping out too much fresh water, you'll pull in salt water, and that's an intrusion. And once salt water gets into your well, it's done. You can't ever use it again. it's over. Okay, so this is a problem in coastal areas of Florida. And you can correct the problem if you build a recharge well and pump fresh water back in. Okay. Then there's also groundwater contamination, and one common source of contamination is sewage. So if you have very permeable aquifers, a lot of people who live off the grid may have septic tanks. Septic tanks leak, and that stuff goes into the groundwater system, and that can be a contaminant, especially their neighbors, perhaps, who have a well and are pumping that water out. But if you have an aquifer that has slow-moving water, where it takes weeks to months for water to kind of move a small distance, the microbes in the ground will purify the sewage water. So it's not a problem. It's only a problem if you have a very permeable aquifer. But there are other contaminants. There are contaminants like gasoline stations have big tanks underground, and they often leak. Gas is a contaminant we don't want in our groundwater to drink. And landfills can spill stuff. You can have trash, effluent, and liquid just kind of make its way in the groundwater. Also, dry cleaners. Dry cleaners use chemicals to clean your shirts and your jackets and stuff like that. So sometimes dry cleaners do the irresponsible thing and just dump those chemicals outside, and that's not good. Okay, so here's that example of comparing two aquifers. Here's the fast-moving aquifer, cavernous, where it takes days or weeks for water to move through the system. And so if you do have a leaky septic tank, that water will be drawn up by this unlucky neighbor who gets to brush his teeth in whatever waste this person produced in their septic tank. Yuck. But if you have a slower-moving aquifer system, months or years, that contaminated water can be purified over time through the filtered and purified by the microbes in the ground. They'll use up all that organic matter, and then you basically get clean water. Yay.